This will be a continuation of the ideas that we talked about on Friday, where we had the flea, I think, on a record player, right? So we're going to continue that idea, and then we're going to get into banked curves. So anytime you're talking about motion on the curve, there are two types of curves. There's an unbanked curve, a flat one, and then there's a banked one, which is like NASCAR kind of thing. So you can follow along in your little handy-dandy little handout there. I'll be doing some little notes on the side, and you guys can squeeze them in there and what have you. So here we have a blue car going around a curve. And you'll notice that the curve has a radius, like so. And do you think that the radius of the curve or the amount of curve matters? Like, look at that one. That one's like a 90-degree curve. Would you have to slow down to go around that curve? Probably, right? And so you'll notice that when there are large curves on the highway, they spread them out quite a bit, right? So that they're a much wider curve. So the net force on a car traveling along a curve is the centripetal force. Fc is equal to mv squared over r, and it's directed towards the center of the curve. For a level curve, the centripetal force will be supplied by the friction force between the tires and the roadway. That's an important concept right there. For a level curve, an unbanked curve, the centripetal force will be supplied by friction between the tires and the roadway. A banked curve can supply the centripetal force by the normal force and the weight without relying on friction. More on banked curves in a minute. Okay, so here we have two pictures of the same car. This is obviously the top-down view, and this is the sort of from the rear kind of view here, right? So the friction force, the centripetal force, is directed towards the center. This green V is indicating that the velocity is forward. Just visiting?
I want to see.
Okay, so this picture here shows the weight force of the car down and the normal force up, right? And you should know that the greater the weight force, the greater the normal force, which does what to the amount of friction? It increases the friction, right? You'll see guys when they're driving a truck, what do they throw in the back in the winter? Tire, snowmobile, concrete blocks, something for more weight. How come? Sandbags to increase friction. Okay? All right. So for a level curve, the centripetal force will be supplied by friction between the tires and the roadway, as indicated up here as well. Here is our first example. What must the coefficient of friction between the tires and the level roadway to allow a car to make a curve of radius r of 350 meters at a speed of 80 kilometers an hour? We're looking for the coefficient of friction. Now, do I have it on the next page? I do. Excellent. For a level curve, the force of friction is the only horizontal force on a car and provides the centripetal force. This can be seen from the free body diagram. Flip the page. F net is Fc is equal to mv squared over r. The radius is 350. The velocity is 22.2. Where did the 22.2 come from?
You just converted it?
I circled it. 80 divided by 3.6 is equal to 22.2, right? The net force must be horizontal, pointing toward the center of the circle, and only the friction force is available to provide it. The normal force and the weight simply cancel each other out. Calculations are easy if the speed is expressed in meters per second, so we do that first. Okay, and now we're going to do the calculations. Okay, so I guess I'm the only one that has to write this out.
So this is just on a no bank.
On an unbanked curve, Jason.
All right.
So, do I know the mass of this car? I don't. Is that going to be a problem, do you think? Yeah? So 22.2 squared divided by 350, and you end up with 1.41 m. What the heck does that mean? 1.41 m times the mass. 1.41 times the mass, whatever the mass is. Right? The normal force is equal to the mass times gravity. And in this case, again, we don't know the mass, we know G, 9.8 M. Right? Everybody with me so far? More or less? Where did this FC come from? Kayla, I need to listen. It's the centripetal force that's being provided by friction, right? The friction force is the centripetal force, which is what it says right here. For this flat curve, the centripetal force is supplied by the friction force FF. FF is equal to mu Fn. You learned that about a month and a half ago. And Fn is equal to 9.8 M. So I'm going to take this 9.8 M, and I'm going to insert it for Fn, and I'm going to get the friction force is mu 9.8 M. What are we trying to solve for here at the end? Like, what are we trying to find out? We're trying to find the mu value. So we've got mu is equal to 9.8 M is equal to the friction force. I don't know the friction force. I do know that this friction force is equal to the centripetal force, which is equal to 1.41 M. So I'm going to make my friction force equal to my centripetal force. What's my friction force? Mu 9.8 M. What's my centripetal force? 1.41 M. And what happens to the M values? They cancel, which means the mass of the car doesn't matter. More on that in a bit. So what is my mu value equal to? 1.41 divided by 9.8, which is about 0.141. This is the mu value that will prevent the car from slipping. Is that a big or a small value for mu?
Average. Big.
Wood on wood is about 0.2 or 0.3, right? 0.25 or so. So that's pretty small. What do you think the mu value is for rubber tires on asphalt road? More or less than 0.141? Way more. Way more. Which means this is more than enough friction to allow you to go around the corner at 80 kilometers an hour. In fact, you could probably go around it at a much greater speed, right? Because if it was a greater speed, then this would be bigger here, which would make this 1.41 bigger, which would make that number bigger, right? Which would make that bigger, which is okay, up to some value. So it says, of course, any coefficient of friction greater than 0.141, like 0.2 or 0.3 or so on. Okay, Heather, you got to make a decision. You're either learning this or you're not. Any coefficient greater than 0.141 will keep the car from slipping. This is the minimum value for mu. Notice that the force of friction is perpendicular to the velocity. It is still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from the center to the right in this diagram if it encounters a patch of low friction surface, like ice or oil, and it will drift, as Zach likes to say. Therefore, the friction force is directed towards the center. Notice, too, that we're actually dealing with static friction. The piece of tire in contact with the road is momentarily at rest with respect to the road, because it's rolling, right? So it's actually static friction. The force of static friction is somewhat greater than the force provided by kinetic friction if the tires start to skid. Once you start skidding, it's pretty tough to gain control because the friction force is less. Let's do another example. Is this on the next page?
Yeah.
Okay. So, we've done one like this. We've done the flea one on Friday. We've done that one just now. This one's a little bit more blank. So, where do we begin? We have a mass of 1,500. We know the radius is 100, and we know that the mu value is 0.65. Are you with us, Hannah?
Yeah.
Okay. How should we start these unbanked curve questions? I suggest you start by reminding yourself that the friction force is equal to the centripetal force.
This one, will we do it like backwards?
Backwards from the previous one, yes.
Yeah.
Yeah. Because this time we know the mu, right? Well, let's plug in what we know. I'm going to sort of set this up a little bit differently. The friction force is mu Fn, right? And the centripetal force is mv squared over r.
Why are you using mu FN?
Friction force is equal to mu times the normal force, because mu is equal to ff over Fn,
Oh,
right? So I'm just rewriting that for friction force, mu times Fn. And that is actually equivalent to mass times gravity, mv squared over r. Is this a new formula? No, we're just using our theory. We're applying what we know about friction and centripetal force and what's happening here. And I've got two formulas. If you want, could we just figure out one and then plug it into the other? Yeah, we could do that. But I kind of like the idea of reinforcing that friction provides a centripetal force. And we're sort of like doing two sides of the equation at one time. Is that okay? Okay, so we know our mu value here. It is 0.65. We know our mass is 1,500 times 9.8. And I guess if I'm interested in making things nice, I really should have my equal sign all lined up. Mass is 1,500. I'll put it in black on this side. V squared over R, which is 100. I've got a nice long equation here, but fortunately there is only one unknown, and that is the velocity, right? Can I solve that for V?
Yep.
Yeah, absolutely. Do you want to do this? What if I multiply it on this side? Would that still work out? Yeah, you'd just be typing times by 1,500 and then dividing by 1,500. Waste of time. Might as well just cancel it. So I'm going to have 0.65 times 9.8. I get 6.37 over here. Here I've got V squared over 100. 100 times 6.37, and it's V squared, so I got to take the square root. $25.2. You mean to tell me I'm going to have to slow down to 25.2 kilometers an hour to go around this corner? Meters per second. Right? Should we convert to kilometers per hour here?
Don't have to.
We don't have to, it doesn't say it, but generally when you're talking about cars on highways, people sort of want to know it, right? So we should probably convert that. So I'm reminding you. So that would be about 91 kilometers per hour. You could safely travel around that curve at just under 91 kilometers an hour. What do you think the highways department, what would Jason's dad put up for a sign? 90? I'm thinking 70 or less, because people don't listen.
It's recommended.
People are foolish. They don't watch, they don't see the signs, they just, whatever, give her. Right? I'm thinking 70, maybe even 60. There is one curve coming through the park just before the big hill, right? And I think it drops to 70, am I right? I've driven around that curve at 80 on a good day,
You're a risky driver.
and I'm a risky driver, Steve, you're right. How did you know that?
Got some intel.
Oh, yeah. So there's a good chance that, yeah, if it's posted at 70, you'll probably make it at 80, but that's assuming a couple things, right? The road is dry, your tires are pretty good, right? And there might even be a little bit of a bank. I think there is actually a bank to that curve, right? It's amazing what a little bit of a bank will do. So yeah, they're going to knock that down considerably for safety. They certainly don't want people driving at 85 around that corner, because if there's anything on the road at all, you're going to start sliding. Does that sort of make sense, that question?
And you're getting that by doing that 3.6 or whatever?
Yeah. Okay, was that hard? What's the basic idea? No. From a solving problem standpoint, the basic idea is that the friction force is equal to the centripetal force. Right? Okay. Now, example number 9 is on a bank curve. Now, the textbook does an absolutely terrible job of explaining this. Okay, so what I'd like you to do is I'd like you to jump to the last page that's here, and then we're going to come back to that example number 9. Okay, so go to that last page there where it says, worked example, a banked curve. Looks like this. Okay, so civil engineers, highways dudes, generally bank curves on roads in such a manner that a car going around this curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round the curve. Suppose that the radius of curvature of a given curve is 60 meters, and that the recommended speed is a mere 40 kilometers an hour, okay, just for example purposes. At what angle should the curve be banked? Generally, they would bank it so that you can drive a little bit faster, okay? Is a radius of curve 60 meters, is that a pretty tight corner? 60 meter radius, do you think? Yeah, that's a pretty tight corner. Okay, they would generally be much bigger than that. Okay, so here's the picture right here. So the center of curvature is this distance here. Okay, imagine that this sort of little block thing here is the car. We're looking at the taillights of the car as it goes away from us. Okay, here's the angle of curvature. You will notice that the weight force, mass times gravity, is straight down like so. Right? And the normal force, this is Fn right here. Okay? Are they equal and opposite? They are not, which means that there is a net force of some kind. Jason remembers, right? Remember all that FD stuff, mg sine theta, and all that kind of stuff, right? Jason remembers that this angle here is equal to that one there. And this one here is the same as this triangle exists up there as well, right? Okay, so consider car mass m going around the curve. The car's weight, mg, acts vertically downward. The road surface exerts an upward normal force F on the car. The vertical component of the reaction must balance the downward weight of the car. So this F normal here is broken into components here and here. This is the vertical. This is the theta, right? This is F cos theta, right? Cosine theta is equal to adjacent over hypotenuse. So this value here is F cos theta. This F cos theta must be balanced by the weight force mg. Okay? The horizontal component of the reaction, F sine theta, this one up here, acts towards the center of the curvature road. This component provides the force towards the center of the curvature, which the car experiences as it rounds the curves. This is, in fact, equal to the centripetal force. Let me grab my notes here. I'll let you just think about that for a second. These are not my notes. Guys, don't lose focus. So this tells me Fc is the F sine theta, right? The F cos theta is the straight up and down force. It is balanced by mg. Does the car accelerate up or down?
It's like, it's the one going across, right?
Yeah.
Okay, I remember that.
Okay, so in other words, F sine theta is equal to, because F sine theta is equal to the centripetal force, that's equal to mv squared over r. This here goes towards the center. Listen, you guys, really, you have to stop the side conversations. You won't get this unless you're concentrating from start to finish. And it's hard for me to explain it when I have to stop and tell you to listen. Just listen for 10 minutes. F cos theta, this one right here, is balanced by the weight force, equal to each other, right? No vertical acceleration. F sine theta is this one here, and it's directed towards the center of the curve. And so because it's directed towards the center of the curve, it's equal to the centripetal force. Centripetal force is mv squared over r is equal to F sine theta. Okay? Now, if you look at this diagram here, if I went opposite over adjacent, that would be the opposite over adjacent is tan. Tan of theta is opposite over adjacent, which is F sine theta over F cos theta. Rewrite that for F sine theta. That's going to be F cos theta tan theta. This gets multiplied up here, right? I'm taking both sides and multiplying by F cos theta. This F cos theta goes up to there. I leave with F sine theta. I flip them around. F sine theta is equal to F cos theta tan theta. It's like doing, what's that called? The trig identity stuff. Remember how much fun that was in math? Let's not talk about that. Okay. What did we say F sine theta was equal to? mv squared over r. What is F cos theta equal to? mg. So F cos theta, mg. Tan theta. Steve is right.
So does math still have anything to do with this, like this whole unit?
Would it be a bad thing if, depending on the mass of your car, you had to slow down to go around a curve? Like if heavy cars had, or if light cars had to go slower around curves, would that be bad? Yeah, right? They can't put up a sign that says, if your car weighs 5,000 kilograms, drive this fast. If your car weighs 7,000 kilograms, drive this fast. It's craziness. Good thing the mass doesn't matter. So the mass cancels out, and what are you left with? I want tan theta by itself, by the way, because that's what I'm trying to find out. I'm trying to find the angle of curvature. So tan theta is equal to v squared, the g goes down here, v squared over rg. And that, my friends, is the formula that you want for a banked curve.
So,
I just derived the formula.
so if there's like a fraction on the one side, you always have to bring it to the bottom of the fraction?
Yeah.
Okay.
Like if it's on the top on one side, it goes to the bottom, right? Tan theta is equal to v squared over rg. That's for banked curves. Do the guys at the highway department know that? They probably learned it at some point, but now what they do is they rely on a big table of values. And I actually have a copy of that somewhere. I had my buddy who's a civil engineer, and we were talking about this one day. He said, I'll send you something you can show your kids. It's like 47 pages, and it's all about, you know, depends on the type of road it is, what kind of vehicles they're experiencing, even the temperature, the climate in that area. This is the simplified version. Okay, so what is our, well, I guess we don't have a question here yet, right? That's our format. Note that if the car attempts to round the curve at the wrong speed, then the difference has to be made up by a sideways friction force exerted between the car's tires and the road surface. Unfortunately, this does not always work, especially if the road surface is wet. This is how fast you can go if there's no friction at all. Is there ever no friction as you go around a corner? Unlikely. Even when you're driving on the highway in the worst winter, there's going to be a little bit of friction. Yeah, that's example 9, right?
Yeah.
Yeah, so let's go back and do...
No, at the top of the page.
Oh, is there?
Yeah, it's going radius 16.
Oh, yeah. What angle? Okay, so this question here should be, do I have room for it? No, I don't. Do you have room for it is a better question.
Yep.
Kind of? Okay, so we'll have to cut corners?
3/4.
Oh, I thought you said we'll have to cut corners on this. That was a good joke.
How do we?
So we're going to do this one right here. 60 meters, 40 kilometers an hour. What's the theta? 60 and 40.
And then
So first step is going to be divide by 3.6. You might, if you want to write this on loosely, if you can. There's no such thing as a waste of paper when you're solving stuff here. 11.1 meters per second. Tan theta is equal to, is it square root? I just wrote it. What is it? V squared over RG. I don't use this one too much. V squared over RG. V is going to be 11.1 squared. Radius of curvature is 60 times 9.8. Now, you may have discovered on your own, I don't know, that when you've got two things on the bottom like this, what do you have to be careful of when you're using your calculator? One way to solve it is to use brackets on the bottom. Right? Well, because if you just go 11.1, divide by 60, times 9.8, what you're really doing is, you're doing this. And is that the same as this in blue? It is not. So how do you do this on your calculator? Or use brackets. Okay, so it's going to be 11.1 squared divided by bracket 60 times 9.8. And then equals. And I get 0.2. What? My angle has to be 0.2 degrees?
No, I used to.
Yeah, exactly. That's the tan theta of it, right? So theta is going to be inverse tan of 0.2.
there we go.
I get about 11.8, 12 degrees. This road has to be banked at about 12 degrees to drive only 40 kilometers an hour. What can they do to make it easier or so that people can drive around the curve faster? They can bank it more, or what else? Increase the radius, exactly. Which is generally what they do. Those curves generally are quite wide. Has anyone ever gone through, if you're going to Winnipeg, if you're going through south of Nipawin there, go towards Carberry, there's like a giant curve. It's huge, right? You actually you turn 90 degrees on the highway, which is unheard of, kind of thing, right? But it's like probably almost a kilometer long, that curve. And then it curves back the other way, right? I think it's like a correction line of some kind. Yeah, just south of Brookdale there's a big curve. Okay, so here's example number 9. How about you give this one a try? Oh, it's almost 3:15 already.
Give it a go.
Give it a go. If you can't do it, that's fine. I'm going to do the answer right away. A race car travels along a bank curve at a speed of 120. It doesn't depend on the force of friction. If the turn is banked at an angle of 25, what is the radius of rotation? So this time you're solving for the R. Go. All you need to do is be able to apply tan theta equals V squared over RG, right? Okay, so we're solving now for the R. I recommend you put in the numbers first. So that's going to be tan of 25 is equal to, the V is converted here for you, 33.3 squared over R times 9.8. Now what do you do when the unknown's on the bottom like that? You multiply it, it goes up there, right? So this is going to be R equal to 33.3 squared. The 9.8 is going to stay down here. And what happens to the tan 25? Goes down here underneath, right? Do you have to be careful because there's more than one thing at the bottom? You sure do. 33.3 squared, divide by bracket, tan of 25, oh, make sure you're in degrees, times 9.8, end bracket. I get 242, 243, I guess. Is that right? Yeah, Jason.
Anyways, so f sine theta, is that still your friction force?
F? No.
No. B squared over r.
No, because F sine theta,
Well, it equals fc, right?
yes. Okay. Yes, F sine theta is the friction force, yes.
Even when it's a bank curve, it's still the same thing?
Yeah, that's how we got here, right?
Oh, sure, yeah.
Hang on, no, it's not the friction force, it's the centripetal force, right? The friction force is actually,
Oh, you said the friction force.
the friction force is actually here, isn't it? Right? Because you're trying to slide out, so it's actually down like that. Now,
So it would
there's,
be like your FD kind of thing?
yeah, there's that as well. If there was no friction, then if this car wasn't moving, what would happen to it? Yeah, it would in fact slide down like this, wouldn't it, right? So there's not only this keeping it on, but there's also FD making it slide down as well. And so there's that component.
If we had to say find the coefficient of friction there,
Ooh,
or is that next level stuff?
yeah. I think there's a bonus question on that, and I don't think that no one's ever been able to solve it. I have an answer for it, but no one, including myself, has figured out how to get to that answer.
But you talk to Jason now. Oh, you don't.
I challenge you, Jason.
Engineer extraordinaire. Yeah. Which one is it? He's got it. I just want to read it.
I don't know, it's on there. It's the last one, last two there, right? Number 7 on the back. If a car curve with a radius of 60 is properly banked for a car traveling at 60, what must be the coefficient of static friction for a non-skid with traveling at 90? Well, there you go. That's a bonus. Yeah, because they are crazy hard. But you don't do that and say, hey, hell yeah. He would have gone at one point.
Oh yeah, not.
Okay, I will stop. I'm done. You're done listening, I can tell. Work period tomorrow. You need to do some work. I think I said Thursday, right?
No.
Test?
Yeah. What?
Aiming for Thursday.
No.
Actually, we should be doing it Wednesday, but I'd be crazy, so I'm giving you 2 days to work. So Thursday.